The 3090.
No, it was 3080, I thought.
3080.
It's already recording. Okay, so I'm gonna share the screen. All right, so let's get started, guys. It's week 3. So we're just gonna do a quick recap of where we are. Okay, so you guys should be seeing Brightspace. So as you know, you have already a homework and a mini project assigned to you, right? So you should all be starting that. So there's a lot of topics obviously going on there. So now on the first week, I kind of just gave, an overall look at things, what this course is about. Last week, we went over Hugging Face, and I just did a lot of examples, right? Of, BERT models. We did some GPT models. So you've seen how that works, and that's, really great. That's transfer learning, right? So we've discussed the definition of transfer learning. So you guys should know that, right? You understand there's pre-training, fine-tuning, and nowadays there's also the reinforcement learning through human feedback. So those are the 3 main topics for this NLP section, right? So you've got your homework, which should be, I haven't created the link, but I did provide, I have the code now posted on here for the GPTs homework, and I think you guys probably found it anyway. The HuckFin one, right? So if you go to that repo, that's the main one. But I think I had forgotten to. Oh, yeah, sorry.
What's the website you said for different books? You said that they have text you can use?
Gutenberg. Is that what you mean? Gutenberg.org? Yeah, Gutenberg, yeah. Yeah, I tested it with Gutenberg, actually. This book is from Gutenberg, HuckFin. So if you click on it, I believe it actually says Gutenberg something. Yeah, Project Gutenberg.
Oh.
So I don't know if the website is there, but.
Oh, yeah,
It's
that's line 7.
line 7. Oh yeah, there it is. Yeah. Yeah, that's a good place to just, scrape some books, get some books. Perfect. All right. So that's your first homework assignment, right? So we'll talk. That's great that you guys have started. Really have fun with that. It's your chance to pre-train. Pre-train if you have, a 2080 or 3080, pre-train for a week. Go ahead, just see what that feels like, right? And then, then you realize, well, llama and everything, those are state of the art because they train on all the data, for many days. So yeah, so anyway, so that's great as far as, what did I do here? Sorry, so if you go back to, yeah, so we are here, right? So in GPTs, right? So here, so I added the code and it's this repo here. I've gone through this one. That's got the HuckFin and everything. You can even ask it questions like, where is Huck? So it's got that prompting and answer functionality as well. Play with that, please. Try the prompt and answer functionality and see where you can go with it. So anyway, this is for your homework, basically, right? I haven't really defined any parameters. At the end of the day, you could, if you want to, just do one file and that's it. But really, it's about, seeing what pre-training is about. That makes sense. Code should work. So let's go back now. I'm gonna close that. All right, so let's go to table of contents. So that's the homework. So I think since you guys have started, I'll think of when we can do it, but maybe at least 2 weeks from now, I'll give you for that homework assignment. And then, of course, the project is the RLHF, Reinforcement Learning Through Human Feedbacks, which is this one. In particular, the RLHF GPT-2 sentiment, right, which was this Jupyter notebook, yeah, that I went through and we discussed it in class, I believe, last time as well, right? So this code works fine, and it produced at the end, this is from Hugging Face, their TLR library, and it produced at the end. You can see that it did succeed in making things more positive. This is, most likely you know, at least 80%, 85% of how ChatGPT and all these, you know, Bloomberg GPT and all these things are being trained. Everyone might have little secrets that they're keep, but in general, and that they're just not disclosing this information. All right, so anyway, that's your mini project. Are there any questions on either the homework or the mini project? Nope. All right. So this is, you know, what you have to do, right? You will work on this. So today, you know, now that the assignments are given and we've done the demos and everything, hopefully you get the gist of how Hugging Face works. So now what we're going to do is we're going to get into how, you know, the theory of it, right? The background of it so that you guys can start to understand all of these things. And that is large, right? So you guys have, you know, took 520. Those of you that took 520 may remember that that's kind of where I left off, right? So I gave a quick, very quick GPTs lecture of 1 hour. You know, we're going to take more time, you know, in this class, as this is more, you know, one of the main topics, right? I was preparing some notes for you guys, so I do have them. You know, I just finished this, so please, if you find typos and stuff, just let me know and I'll correct them. But there are definitely typos in there. Okay, but you know, so I've been I'm not gonna lie to you guys. I've been working on this transformers thing since 2018, like trying to wrap my head around it. Right? It's you know, you have your deep learning algorithm or even a CNN. That's easy compared to the transformer. Just the jump in complexity is really high. So there's a lot of concepts. So we'll go over that. So basically, as far as going through the background, you know, I haven't added the RLHF background yet, but I gave you the translation paper from Vaswani, so hopefully you started to read that. Read it, please. Okay, you should read the original paper. So hopefully you started reading that, and then I have my notes. So I will be talking about BERTs and GPTs, obviously. So mainly, not so much the translation from one language to the other. Since we've used BERTs in last week, and we also used GPTs last week. Okay, so basically today is, as I said, background. So I've prepared, I have these, basically this, so I put together this website for you guys. It's from my book, but it's chapter 10, and I've made it available online for free. So, you know, you guys can use it. And it's basically my attempt at explaining this topic in a lot of detail. So you might remember these graphs from last semester. I've now updated everything, so it should be consistent code and graphs. All right, so we're going to start basically, and you can read through this. So this is, you know, chapter 10, transformers, and it covers basically the main ideas of the transformer. Remember that a lot of linear algebra and, you know, tensors are basically part of this. There's the attention mechanism, which is one of the most important ideas. There's ideas on embeddings, masks, positional encoding, just the tokens themselves. How to get the tokens is a process. So I'll start to talk about that, but there's algorithms for that as well. What are inputs and outputs? Then the GPT, right? So what part of the transformer is the GPT? Teacher forcing, which is another concept. And then basically the code that you guys are running is explained here in as much detail as possible. Okay, so I'll go over this, some of the ideas, but this is you can see literally the code that I gave you on the repo. So hopefully every little aspect of this is explained. If something is not clear, let me know and I'll see what I can do to, you know, I can say that at some moment I understood this completely, and then over the days I kind of forget it. So it's basically a good way to write it out and have everything written there. So definitely read through this, okay? Remember that there's the architecture. Basically, this class here is everything. This is the heart of the transformer that brings together everything else. Okay, so the class called GPT model. If you notice, this is very consistent with how you learn to code PyTorch in 520. So that's the nice thing about that. It's extremely consistent. You can see it's got all the details of it, all the diagrams. So we'll go over this today. And so that's basically here, the main thing that's described is how a GPT works. Okay, I think some of the examples. Then encoder-only models. So encoder-only models are the BERT models, okay? So you know, basically here I'll show the main difference. It's actually funny because there's not much of a difference there. So we'll go over BERTs, and I put together some graphs of how you train the BERTs. So we'll go over that idea. And then a little bit on encoder-decoder transformers. So this would be the actual whole transformer, which was implemented by Vaswani. And then basically I'll highlight what's important here. Now, data wrangling from scratch is basically, you know, what if you had your own data? How do you make it into the, you know, the tokens? How do you create the dictionary, the tokenizer? That's this, okay? Now, nowadays, we don't do that. You know, you'll use sentence piece or BP or something like that. But if you want to know how, you know, this is an attempt at that. All right, so we can go over that as well. And that's basically pretty much all of transformers. So hopefully, as I said, this is clear enough. But, you know, we'll start with that. Okay. All right, so transformers, right? So here is the original. So hopefully if you've read the paper, this is the original architecture. It's very important to note that the architecture hasn't really changed that much. Like it was you know, I think I've told this story. It was invented in 2017, published by Google, made public, and it was really done for language translation. And really, you know, honestly, they probably didn't know what they had, and because they would have kept it secret if they had known. Really from there, a lot of research has gone into this, like crazy amount of research. Millions of dollars have been spent. But you can see here, this diagram shows the original transformer, which was basically for language translation. So you would give it, here you can see you have what is referred to as the encoder, which is this one. Actually, the encoder would be the orange highlighted thing. All right. And then the decoder is this other one over here. Okay, so this is the architecture. The code that's in here basically is this whole thing. All right, so all the GPT, and then you should be able to figure out, all the decoder, I should say, is the GPT. And then you'll see that once you understand the decoder and the GPT, if you look at the encoder, it'll just click because it's literally the same thing. Okay, only a few little tweaks here and there. So we'll kind of hopefully discuss that. What happens is you give it the English sentence, but you also had to give it the other language sentence, which in this case was, let's say, I think Portuguese was in the original paper of Vaswani. Now, one thing that's really important that you'll see me do everywhere is these dimensions, okay? Like the dimensions of the tensors. That's a really good way of understanding things. So last semester when I did this, if you remember, the code did not match, but now the code matches these diagrams. So hopefully it'll make more sense. All right, so you start with an English sentence and it goes through this box where a couple of things will happen. One thing is initially you give it words, well, you'll give it tokens, right? The tokens can be words, subwords, letters, as in the example that we have in the repo, etc. Usually these are calculated through specific algorithms, right? And so, and it's a bit challenging, but that's what the data wrangling section here is for, so that you can actually see how you could do it, although sentence piece and those algorithms are their own efficient implementation. But basically, you start with an English sentence that becomes a set of IDs. Notice that the input is n by 40. 40 here means the size of the sentence per se, right? So transformers are not variable length. All right, because of the fact that they're going to go into the GPU, they need to be fixed length. It's like, imagine it's like you have a box and it's always that box that goes in, or like an image almost, where we want images to be, 32 by 32. Do you guys see that? You can think of a transformer that way. It wants that. It needs that to work. So you can think of the rows as the actual inputs, as a batch. You can think of it as a batch of sentences, basically. And you can think of the columns as the actual tokens that you would put in there. So obviously sentences are variable length, right? So I can say the car is, or you could say the car is going really fast and blah, blah, blah. So what you do there is you need to set a size for the length of the sentence. So you kind of say, my sentences are not going to be larger than 40. Okay. Now, if you guys need more, you can just go into the code that I provided and change that. It's a parameter at the top that says 40. And because, the reason why I'm using 40 here is because the original Vaswani paper, if you've started to read it, is 40. And so I'm trying to be consistent with that. So there's like that connection. But what happens is as you have 40, it's either going to be truncated if the sentence is longer than 40 or padded if it's shorter than 40, right? And so the padding is a tricky thing that requires masking, all right? One of the things that it's best to understand with a few examples later. So there's a couple of things like positional encoding and masking that I'm kind of leaving for later, all right? Because they can be a little bit tricky to understand, but everything else should be pretty straightforward. All right, so if you notice here, the sentence, notice here is n by 40, and then it becomes n by 40 by 512, n by 40 by 512. 512 is the embedding size. And what that means is that every word, or every token, I should say, when you hear me say word, subword, syllable, token, I mean the same things. I may be making a mistake, but it's the same thing. It's every word which is an ID is going to be a number, as we will see later, like 17, 3, 57, and so on, right? But transformers need a representation of that. So the way that you do it is by doing a vector space type of a representation called an embedding. So you define that you're going to say, you know what, every word or every ID is of size 512. Okay, so you're going to represent those. So I'll give you the example of people, right? So we're going to represent people, right, by their age, their weight, and their height. Okay, for some reason. So now we create a vector space of 3 dimensions: height, weight, and age, right? And every person can be represented by that. And that's a vector of 3. Would you agree? Right? You just ask the person, hey, what's your height? What's your age? What's your weight? And boom, that's your representation. So you are and initially you were not Bob or Mary or whatever, you were ID 3 or ID 65 or ID 955. Do you see that? That's how you start. Every person starts as an ID. But then it's going to go into this vector space called the embedding. And that embedding space is going to be height, weight, age. Those 3 parameters. So that embedding is of size 3, okay? But here, and that's exactly how a transformer works. And the only difference is you're going to say, yeah, every ID is going to be represented by a vector of a specific size. In this case, 512. Do you see that? So this is very easy nowadays in PyTorch because PyTorch has an embedding element, object, that allows you to do that very nicely, and you will see that later. But the key thing to understand is through a neural network, you're going to start with from n by 40 and make it n by 40 by 512. Every one of these, so you have a batch, let's say, of 16 sentences that you grab. This can be 16 sentences from Shakespeare or Huckleberry Finn, right? And then you have 40 of those, and then each of those is no longer ID 7 or 32, but embedding of size 512. Just like we set for people, embeddings of size 3. Now, the question you might ask is, okay, that makes sense, but how do I ask every ID what each of these 512 values are? And the answer is that you don't, right? The transformer will learn these embeddings on its own. This is why it needs a lot of pre-training. So it's going to go through, give it inputs to predict an output many, many, many times. And what's going to happen is these values, so you got one ID in here and you've got its corresponding embedding of size 512. That's going to start as a random value because you can imagine it's like random weights. But at the end of training, there's actually weights there that are relevant to the problem that you are trying to teach it. Does that make sense, guys? So the weights here are learned by the transformer. They're in there somewhere in the architecture. Every time you give it input, it goes all the way. In fact, I would say an encoder is nothing more than an embedding machine. So it basically does that. It can produce embeddings at the end. Okay, so keep that in mind. These, I think I was very consistent in these dimensions because this is how I understand the transformer. But you can change these values. Okay, I think this 40 can now be like 1026. I mean, if you have enough powerful GPUs and things like that, the bigger it is, probably the better. And the embeddings could also be bigger, but to fill in all that data or all those embeddings, you need a lot of data. Okay, if you notice, that's the same here and here, right? The only thing that's kind of the sizes are the same. It's just that there's a few special things going on. There's also, so if you notice, it says apply embeddings and also positional encoding. So this is another technique that it's used so that so basically the embedding of N40 by 512, there's an additional embedding of N by 40 by 512 that includes the positional information. So that is to say, if you have a sentence, you need to know that for the car is going really fast, the comes before car. Really fast comes after car, and so on. Okay. Now, once you do that, you have the embedding of N40 by 512. It starts to go, it goes now into the encoder. And the encoder is nothing more than these blocks called encoder layers. So you have 1, 2, 3, 4, 5, 6, which were the layers in the original Vaswani paper. You can look that up. It's right in there. Okay. So you have encoder layer. Now, the thing that to keep in mind is that it takes an input N40 by 512, and the output is also N40 by 512, right? This is an important thing. It's a neural network that regardless of what goes in, well, I mean, that you could maybe say that you don't even need to know what's in here because you put in N40 by 512, you get out N40 by 512. And that N40 by 512 becomes the input to the next layer, which also produces N40 by 512, and so on. And you do that 6 times until at the end you get an N40 by 512 embedding. Okay, that's it. So there's this is a lot of layers of a neural network. This is very deep. Okay. Now notice that this has no meaning. This is just numbers that are N by 40 by 512. Now, you give it the English and the Portuguese, right? And it does the same thing here. And then those go through decoder layers, which are almost exactly the same, except that now they need to account for the fact that the encoder output becomes an input to these layers, okay? And that output of the encoder, the English context, goes into every single one of these decoder layers here. So it goes in, it goes in. It gets, so now you need to have in here, and we'll see that in the very end, there's an additional mechanism that can take whatever this decoder produces, but also what came out of the encoder. So you need to have the information from the encoder and the information from the previous, and that brings it together, okay? That's the one thing that the whole transformer needs to have that the encoders or the decoders alone do not need to have, because they don't work together, right? They're independent. So that's why I think it's better to try to understand transformers by looking at either encoders or decoders, okay? And we will start with GPTs, And then I think hopefully once you understand GPTs, encoders will, BERTs will make a lot of sense. It'll be very, very similar. Okay. Now keep in mind, whereas the encoder, then this is really important because it's actually in the code. The encoder does not have anything and just produces N40 by 512. The decoder we have here, there should be 6 also. Yeah, there's 6 blocks. But if you notice, the last one is a linear layer. And this is actually the layer that you saw all through 520. It's just a normal, fully connected neural network layer. And notice that this final layer is necessary so that you can take an N40 by 512 and convert it into an N40 by vocabulary size. Why vocabulary size? Because this is the logits. This is the place where you're predicting the next word in the sequence. Does that make sense? That's really what you're going to do. Okay. So basically, this is the logic of the overall transformer. Any questions, guys, so far? So this is the architecture. Okay. Now, as I said, the transformer currently is the most advanced. It came out in 2017, but really, I don't know this part of the story, but researchers just started looking at encoder only, probably to understand how it worked, is what I assume. And some other people said, no, let's just focus on the decoder part. That looks interesting to me. So they literally just imagined, they just broke it off. And the only thing that they removed is this, what represent this blue line here. The mechanism in the decoder that takes both the encoder output and the decoder output from previous layers. That's really honestly the only thing that was taken out. And then after that, it's basically, this encoder is literally how it came out of the original paper, and the decoders just detach that part. Okay. That's it. All right. So now, hopefully, that's kind of the intro of what I'm going to discuss, of how I wanted to present this. Now I'm just going to focus on the decoder layer, right? So really, this is the one that we're going to go through. And actually, this is the homework I've given you. I didn't give you a homework of like train encoders, for instance. You could, and I'll show you how they were trained to create the BERTs. It's very interesting. But really, let's go through the GPTs here. So there's a couple of things that I didn't mention here. There's actually a difference in when you're doing the whole transformer, that if you're training versus testing, right? Something called teacher forcing. It's a trick, okay? And I didn't mention that, but I'll mention that. It's a little bit difficult to see initially. So let's wait on that one. But just keep in mind that when you're training the whole transformer, there's a trick called teacher forcing. That's applied when you're doing training, but when you're doing testing, you don't apply it. But we'll talk about that later. So here's my notes on this. So transformers, I've mentioned all of this. They were first made popular in the paper "Attention is All You Need" by Vaswani et al. Of 2017. Please read through that paper. I would recommend that you do that. They are very interesting and seem to be very powerful. In the past, before transformers, everyone did research in recurrent neural networks. Okay, these were the dominant architecture. I mean, you still use that sometimes for sequential data, but they basically had a few problems, and transformers have just become way better. Obviously, they've here are the papers. This is the original BERT by Google, by Devlin et al. In 2018. So you can see it came out like a year later. And in Radford 2019 had GPT-3, where they started to show real improvement, basically. And of course, most notably, ChatGPT of last year, I think it came out, if I remember correctly. And, that has been quite interesting. So initially, before we saw ChatGPT, transformers were being used for, what does it say here? Language translation, question answering, document summarization. You've seen examples of this, actually, where we look at the Hugging Face example. automatic code generation, text generation, etc. Right? So all of this is in the examples that we did last week with Hugging Face. So that was pretty much as far the state of the art back then. Kind of impressive summarization, kind of impressive this and that. But obviously, something like ChatGPT was very different because it had this additional RLHF, right? So this additional functionality of your mini project. All right, so basically, we've talked about how you get these things to work. So you have the pre-training, we have transfer learning. So we have pre-training first, and then we have fine-tuning, basically. So pre-training requires a massive amount of data, and then fine-tuning requires very little data. And this is kind of where the mini project, you're using basically fine-tuning. You will use a pre-trained model, but in the homework, you will pre-train, right? So you can give it as much data as you want. I mean, if you had all the data and all the GPUs, you know, make your own llama, for instance. Okay. Yeah, so basically, as I say here, a transformer network is trained on all data you have, you know, literally all the text in the world if you have it. I mean, they've actually gotten to the point where they're worried that they're going to run out of data. Like, you know, we're actually going to read all the books, but then there's synthetic data. The fact that you can create a couple of Chat GPTs to generate new text and train on that, you know, so there's always a lot of ideas going around. The process requires massive amounts of computing and can be very expensive. The most notable currently, you know, GPT-4, I think, is where they're at. I honestly don't know. Llama models are very, it's basically for all of you, this is the thing that you can use. I believe Hugging Face now has llama models somehow. There's a lot of tools out there. There's even a C version, like pure C, to grab llama weights, load them into memory, and you can go build your robot or whatever you want because it's pure C. You can build literally anything. And I think it's done with like 1,000 lines of code. So there's a lot going on. People, you know, are definitely working hard on this problem. That's in Andrish Karpathy's repo, by the way. All right, so then, you know, so we've talked about pre-training and fine-tuning. All right, so then, so here are some of the main ideas of the transformer. You know, NumPy arrays, tensors, and linear algebra. You know, you got to try to master this stuff, the NumPy operations. So definitely, you know, that's why we did that in 520, right? We did some NumPy examples. The attention mechanism is really one of the most important things in the transformer. This will take a little bit for us to understand, but it is in there in the code, okay? So I'll come back to that. Currently, as I said, I'm just giving you the idea. So the attention mechanism in transformers is the heart of the whole algorithm. It's nothing more than a dot product matrix multiplication. So a way that I haven't been able to create like a graph of this or anything, but basically imagine so let's think of this, right? What's the size of the input? It's n by 40, right? So then that right there tells you that the attention matrix, this dot product, will be 40 by 40. Do you guys see that? Why does that mean? It means that you take the 40 inputs and compare them to themselves, right? Or to other things. But whatever you have, you're creating a 40 by 40 matrix. And you just put it at the heart of the transformer. And as it's learning, it's going to learn to associate certain words with other words. And it does that automatically. That's what the neural net does, okay? So the attention, we'll come back to this idea, but the attention mechanism in transformers is the heart, is nothing more than a dot product multiplication between all the tokens, you know, e.g. the words, syllables, subwords, etc. In a sentence, the idea is that given the input and output, the model learns to correlate the words in the sentence to determine their importance. Okay, so, you know, I think I gave this example before that, you know, the bank of the river or the rivers rob the bank, right? So those are different words. And so you want to have different embeddings for bank when it's related to bank of the river versus bank when it's related to a financial institution. And that's what the attention mechanism can actually give you. All right. It finds weights between these. So it's going to say, you know, whenever I see river and I see bank, it has this meaning, like a slippery, sandy thing. And whenever and it's in the network, right? And that's a type of understanding, right? So that's why people think, you know, there's some intelligence in there. And then when it sees the robbers rob the bank, you know what? This bank that they speak of, this ID, right? Which remember, it started as a number, but became a 512 embedding, right? No, it does not mean bank of a sandy thing. It means a financial institution. So I'm going to create a different embedding for that. You see that? So that's really important because if you think about it, what's happening here is you put in, imagine that ID 7 is bank, right? Okay. But it's in the context of Bank of the River. So it's going to create an embedding of 512 with a set of numbers that represent financial institutions, banking system, those kinds of things. Whereas if you get bank in here again, but this time is the bank, you know, the people were walking on the bank of the river and it was slippery. When it takes that ID 3, let's say, and it creates the embedding of 512, it's a different embedding. Because now this embedding should represent slippery things, right? So, you know, bank of the river. Does that make sense, guys? This is really important. You know, before Word2Vec, which was 2014, would take bank, just one word bank, and you would have a really nice embedding. But it was the same embedding if it was Bank of the River or if it was bank, the financial institution. Same embedding. You can literally download that embedding today as it was trained over the whole internet. So that was 2014. That was an amazing thing, actually. You know, for 20, 30 years, it wasn't done that way. And then in 2014, they started doing embeddings. 3 years later, attention allows you to create an embedding, but now each version of bank has a different representation. That's what's really important. Now, keep in mind that the word bank may be broken up into parts, like BAN and then K is another thing. Those two embeddings capture information that works together, right? And all of that is done by the neural network. Do you guys understand? Does that make sense? Really important, right? So this is one of the key things. A lot of people use encoders just to create embeddings, right? So they'll go and they'll run a whole bunch of text through the thing to train it. And then once they have a new word or a new sentence, they'll run it through the whole thing. And maybe at this layer or at this layer, they just extract whatever that embedding is. It N by 40 by 512. And they have it's basically, you know what a lot of people are calling this these days? Compression. This is, you know, you guys, you know, I'm sure studied compression at some point, right? We all know what compression is, right? Lossy compression, lossless compression. That's what the state of AI and LLMs is today, compression, according to some people. So basically, these techniques, all they're doing is they're taking information and compressing it into these embeddings. Okay? So it's an interesting concept. Okay, to think about, like more philosophical, I think, but very interesting. All right, anyway, so hopefully that made sense. All right, so that's one of the key ideas. Embeddings, I've talked about embeddings. So sequences of tokens in a sentence are converted into sequences of IDs. An embedding approach converts the sequence of IDs into a sequence of embeddings, basically, that you have. So it starts to create a tensor in memory, right? You know. And so you know, this is kind of what I said. So you go from n batches and tokens to a 3D tensor of size n batches, n tokens, embedding dimension, right? So n by 40 to n by 40 by 512. So it goes from 2D to 3D. Okay, so that I think hopefully that one is easy to visualize, and that's just a neural network basically doing that. Masks, it's another one. So we'll come back to this one. I kind of wrote this as an example of the translation thing, but it's used throughout, right? So masking is important, but basically the idea is how do you mask a specific word efficiently? So I have the cat is masked on the couch. How do you mask that? Well, you could keep track, a variable that says the fourth ID should be masked, and then a for loop is going to go through it, and then when you find it, mask it, right? What's the problem with that? The problem is we need to run this efficiently on a GPU. You see that? GPUs don't work with for loops very well. What do they need? Matrix multiplications, right? So if you have a good example of this, just for one sentence, a 1 by 40, right? And you need to mask the third one element in that 1 by 40. Something easy that you could do is just add another vector that is 1 by 40, where everything is a 1 except the third element, which is a 0. So effectively, when you multiply those two together, you zero out one of them. Do you see that? That's masking. Does that make sense? And this is important because now you can train a transformer or a GPT through a GPU. You just give it the input, n by 40 by 512, and the mask, n by 40 by 512, with the ones and zeros relevant to what you need to mask. Does that make sense? And so you can just like erase things without actually modifying the data. Okay, because you can perform this matrix multiplication. Okay, so that's masking. That's an important concept. Positional encoding. So these are the two concepts, mask and positional encoding, that I will cover later. But just keep in mind that positional encoding just deals with the fact that you need to know the cat is sleeping. So sleeping goes after cat, the goes before cat, right? So you need to know which words come after which. Obviously, when we speak, we speak in a sequence, right? So we also need to do that. Nowadays, this is just one line of code in PyTorch, so it makes it very easy. But we will come back to this one. Let's talk a little bit about tokens. So as I said, this is the one term that I will, I sometimes say letters or syllables or words. The right terms is probably subwords. But some people say tokens. So in a GPT, we want to predict the next word given previous words. However, to improve performance, transformer models do not predict the next word. Instead, they predict the next subword. So a good analogy of subword is syllable. But the thing is, syllables are things that we know from school, right? We went to school and we learn about syllables. I mean, that's literally like second grade or something, right? So you're learning about syllables. But so a good analogy of subword is a syllable, although transformers do not use syllables either. Instead, these subwords are calculated based on specific algorithms, such as something called BPE or another one called sentence piece. There's a couple of libraries for this. One is called tick token, I believe. So there's several ones. Actually, the code uses letters and it's done from scratch, right? And then the section that I call data wrangling also tries to do that for words themselves. But you don't use words, you don't use letters, neither one. So letters would be like at the very low end and the full word would be somewhere over here. Instead, you use something in the middle, more like a syllable, but instead it's a subword where this thing is created by the algorithm. So it could be something like, what's something that's not a syllable but could be a subword, like AC, right? That's not a syllable, is it? AC is not a syllable, but it could be a subword. Why? So how is that determined? It's determined based on the frequency of occurrence. So that's why when you're training a transformer, you're going to have two passes. You're going to have the tokenizer first to create the vocabulary, and then you're going to have the once you've created the vocabulary, then you're going to train the transformer. So you have these two things. So basically, in the creation of the vocabulary with the tokenizer, you do this based on frequency of occurrence. So the most frequent things, and this kind of a good analogy of this is Morse code. So you guys, I'm sure have heard of Morse code. So in Morse code, you got D, 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 So the E, or no, the E would be what? A lot of D, 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 or just a few? What would be a good idea? 1. Why 1 and not 7?
It's most common.
It's the most common, exactly. So it's the most common letter, right? So if you make that also the most lengthy one, then it's a problem of so much information, too much information being used, right? And so that's the same thing with the algorithms. They use the same idea, right? So they try to, so you'll find that in the vocabulary, everything has an ID, and the lower IDs are going to be the most frequent terms, and then the higher IDs will be the most infrequent terms. Does that make sense, guys? So that's a good analogy. Pure information theory right there, right? So it's everywhere, right? Claude Shannon's work. All right. So anyway, so the two algorithms are BPE and sentence piece. I mean, these are tough algorithms to understand. I can tell you. They're tough to understand, but they're implemented in C code to be efficient. So, but there are libraries for them that you can use. So now here's the reason also why you do the syllables. So this allows the transformer to learn to generate new words never seen before, right? So I tried to create an example here, maybe not the best one. So for example, it may have seen the dog is playing, right? So it's seen that in the vocabulary, play and ing, because those are frequent. Ing is a frequent ending for things, so it might create a subword for that. And then it knows that play, becomes like a root of a lot of words. So by breaking the word into subwords, such as play and ing, it can learn to generate new variations of words it never saw before, such as, well, the lady is iPhone-ing, right? So you would understand if I said that. Are you iPhoning? Maybe a bad example, but that's kind of what I'm saying, that, the algorithm can actually do this. That's pretty impressive, right? That, a transformer literally, it sees a word and it's seen it in some context and no, she's iPhoning. And we as humans might be able to grasp what that means, that it's like she's using an iPhone, because it learned, now it never saw iPhoning. It's never seen that word, may not even exist, but it's able to create a sentence that is like that and is correct just because it knew playing, all right? And so that's the context or the idea of why you use subwords, right? So it's, that's basically it. All right. So we intuitively know what it means, and the transformer apparently has some understanding of it. So the fact is that tokens can be words, syllables, subwords, letters, but generally this is basically subwords, and you use this BPE algorithm or sentence piece. Don't worry about understanding those algorithms. I mean, they're outside of the scope here. So inputs and outputs. So I've talked about this. I kind of explained this initially. So, one good thing about this is to think of like images. This is kind of how I like to think about it. So we know that we want images to be 28 by 28. So you define a fixed size, right, for the sentence, something such as this. This is an actual example. And so what happens here is that this is basically called padding. So your input is always 40, let's say, and then the sentence is just the first part and the rest is padding. How do you pad it? Again, you could do something like this. You can have a mask, etc. But at the end of the day, the mask can also help you to do padding. All right, this is another one. I think this one is longer, and it just shows that you just do the pattern. All right, so any questions so far? So those are the main ideas. All right, now we're gonna dive into the GPT, right? So this is homework 1. Hopefully you guys are working on it. At the end of class today, I'll give like 20 minutes or so, and we can discuss the homework if you have any developments or anything like that, so we can get a sense of how things are working, okay? So here's the same diagram as before, but if you notice now I have this arrow, red arrow, that's the GPT. So you literally drop this whole thing, it's gone. So what's great about that is this blue line is no longer there. So you're no longer getting an encoder output, okay? That means that in the decoder layer, you can drop that mechanism. There isn't, you'll see it later as we dive into these layers, that there's a mechanism that handles encoder outputs that is dropped. But otherwise, the architecture should be the same. So GPTs, you saw the paper from Rutherford, I think Radford or something. GPT stand for Generative Pre-trained Transformer. So the idea is that this is you all often hear generative AI, right? All this generative AI here and there. It's really just things that generate data. It's one of the topics we'll cover this semester is GANs and conditional GANs. So you guys will see, we'll generate some images, a 7 or a 6 or something like that. That's a generative model. Okay, something that generates, it learns how to generate. And here, GPTs generate text. And you guys saw this when we looked at Hugging Face, right? And GPT-2 was able to generate text. So that's where the name comes from, okay? So GPT uses the decoder only part of the transformer. So the input to the decoder varies based on whether you are training or predicting, okay? And this is the thing that I was saying that can be a little bit confusing at first, because not many people will make this distinction. So you'll understand how you train it, but then it doesn't make sense how to test it, or you understand how to test it, but then this just doesn't make sense, right? Now, the reason why you don't use the same mechanism is when you're training, the model's predicting. Do you guys see that? But you use that prediction to train in the next step. What's the problem with that? Think about it. You've trained the transformer for an hour. It's generating outputs that you're using as inputs to train more, to produce more outputs. Do you see that cycle? So you have a transformer, gets some inputs, gets an output, comes back. What do you think about those outputs in the beginning? I mean, initially the weights were random, right? So those outputs are pretty bad. So why would you want to use those outputs? Because what's going to happen is they go into the transformer and it's garbage in, garbage out. You see what I'm saying? So during training, you don't want to do that because the predictions are already kind of bad anyway. Why would you give it that? So instead, you do this thing called teacher forcing, where during training, you don't use what it predicts, but instead you use actual good data. Like you need to say, this is the input and this is the output, okay? That's the difference. Whereas when you do testing, you obviously go in and then whatever it predicts, right? That's what you use. Because remember, you're doing a generative model. So you're saying the cat, okay, goes in. The cat is, right? So the cat is sleeping. You see that? So that is happening. Okay, so that's a really important thing to understand, and that's the idea with teacher forcing. So the input to the decoder varies based on whether you are training or predicting. If you are training, the input to the decoder is the sentence itself. So the same sentence that you give it as input is also what you give it as output. Except for one thing, they're shifted. And the reason for that is that you want to predict the next word. So basically, it's like you're saying, I'm going to give you the sentence, the cat is, and then you have to tell me also over here, the cat is sleeping, right? So they're basically the same sentence, just shifted by one word like that. Any questions on that idea? I do have an example later on this, so just keep that in mind. So when training, a mask is needed here to prevent the model from seeing all the words. So this is something that you can do. This is called a look-ahead mask. If you are testing, the input is just the previous word before the word you are trying to predict. So you start with a start of sentence token, e.g. something like, oh, I forgot to include e.g. But it would be something like start of sentence, basically, okay? So start of sentence is just a token that you would give it, and then you would predict. So you give it start of sentence, and it'll probably say the. So in the previous example that we did, I gave it 1, 0, then you also can give it a sequence of IDs. Whatever you do is going to produce a whole bunch of, it's going to start producing from that. The predicted word is then added to the previous tokens, and the process is repeated. Okay. All right. So the original decoder from Vaswani had 6 layers called 6 decoder layers, which are basically this. And this is, this diagram is, is based on the original paper. And honestly, this doesn't change that much. And then it's followed by a fully connected layer. So this is really important, and we will see this in the code as well, okay? So there's going to be in the code a section to start, a section for embedding, a section for positional encoding, followed by 6 decoder layers, followed by a final linear layer to produce the output. The full architecture of the decoder can be seen in the following figure here, okay? Any questions? So this is going to be, we're going to look at how, and this is the code you have. Basically, it's an implementation that matches this exactly. Now, each decoder layer consists of a decoder multi-head attention layer, followed by a fully connected layer. So there's going to be fully connected layers inside each decoder layer. Now, the attention layer consists of M heads, which are 8 parallel attention sublayers. So this is difficult to understand initially, but we will see this in the code as well. There's actually not one attention that is done. The 40 by 40, that's actually done 8 times. And the reason for that is it's almost like we can think of it as people, right? So you are one attention, you're one attention, you're one attention, you're all one, maybe you're 8 attentions. So the idea is you all look at the sentence, but you may look at it differently, right? So you get the data and you learn something and you learn something and you learn something. So all of you learn something about this attention. You see that? And that's it. So you create literally 8, and you could have 1 matrix multiplication in there, but you have 8. And then once you guys produce the output, those 8 are concatenated basically, and they form one single attention. Do you see that? That's this part, which is also in the code that we will need to see, okay? So the attention layers consist of M heads, which are parallel attention sublayers that are later concatenated. The numbers 6 and 8 here are a choice of the architect. So it's really, I looked into this, and I think it was just in 2017, that's what a GPU could efficiently do. Okay, probably if they did it today, they would have done it with something a little bit bigger. Okay, now this is nicely implemented in the PyTorch code in such a way that you can create more if you want. Just keep in mind, I need to say this. This is the part that is time consuming of the GPT. And this is actually one of the limiting factors of transformers and GPTs, because it's a matrix multiplication of 40 by 40. If you could say, what if we made it 512 by 512? Well, it's a matrix multiplication of 512 by 512. If you made it 40 by 80, that's a matrix multiplication of 4080 by 4080. You see that explodes in that multiplication is very resource intensive, the bigger it is. So this is what limits transformers today, okay? And people are researching this to find efficient ways of doing it, because it literally explodes, right? So, it's a square matrix, basically, okay? Do you guys see that? So anyway, we'll come back to this idea. Today, I'm just going over like main ideas, and so you understand what everything is. I think I talked about teacher forcing already. I didn't teacher forcing. Okay, yeah. So teacher forcing is that in the training, right? In the training, you give it the sentence as input and output. You don't actually use what it generated. So the idea was that you don't want, so you give it an input, it produces an output, right? But then you would use that output as input for the next token. The problem is, as I said, when the transformer has just started, it's got bad weights. This is random weights, actually. So the output is almost 100% guaranteed to be a bad one. So it's gonna, so, okay, let me give an example. You want to say the cat is sleeping, right? What's going to happen in the beginning is going to say the cat, car, bird, 11. You see what I'm saying? So you do not then want to train it with the car, bird, 11, because then the next time it's going to say the car, bird, 11, 25. You know, it's just, it's bad information. So instead you do the car, the bird is, or sorry, the cat is sleeping on the couch. The cat is sleeping on the couch today. You see that? Teacher forcing basically means that you're using the same input as output, only shifted, because you only want the next word. So, and I kind of wrote this. You may have already read somewhere that the decoder in the transformer network predicts one word at a time, and that word is read back as an input in the next generation. But also the network predicts the last word in the sequence of the words. So what is going on here? So as it turns out, the mechanism of predicting one word at a time and feeding it back into as an input in the next iteration is only done during testing, the testing phase. And it's not done during training. Instead, during training of a decoder, we use teacher forcing. Teacher forcing is a technique where you do not use the predicted outputs of the decoder to feed back as input, but instead you use the real data, okay? And this helps the model to learn the correct information instead of its own erroneous predictions, especially at the beginning. Does that make sense, guys? That idea? Any questions about teacher forcing? All right, great. So that's an important one, okay? So that's all the main ideas. All right, so now the next step is we're going to start getting into the code. And this is literally the code, the Huckleberry Finn code in the repo, the one that you guys are using for your homework assignment, right? So you're basically taking a pure GPT and you're going to pre-train it for the homework, which is much data as you want, right? So you're going to implement this entire architecture, okay? And that's what that code is, all right? So we'll just now, as you probably started reading through it, you saw it's quite complex, okay? So the best way to think about a GPT in PyTorch from scratch is that it's very object-oriented. That's really the best way to code it, right? So this is why in 520, everything was object-oriented. If you remember, you know, simple things may have been harder at the beginning because it was object-oriented, but at the end, it starts to make things easier. When we implement a GAN later this semester and a CGAN, we will also take advantage of object-oriented constructs, right? If you remember, we always had the init and the forward, and that's really helpful to understand transformers, okay? Also, another thing to look at some point, I may show you some an implementation of a transformer in 4 years ago. 4 years ago, it's much more, there's much more code in there. So you have to keep in mind that PyTorch has created a lot of constructs already, okay? And that makes the code one line instead of 30 lines, okay? So we actually, even though we're writing in PyTorch, we're not at the low-level API of PyTorch. We're at a higher-level API of PyTorch, okay? Still a lot of flexibility, but there's a lot of constructs that have been made that's really nice. So So this code uses those high level API constructs to make it more readable. The other one might be a little bit more complex. So in this section, we will implement a GPT using everything we've learned. The code will be very object-oriented for efficiency. That being said, this GPT is implemented from scratch, works really well, and can be scaled. This is actually a pretty good code. Andris Karpathy actually developed this code, so I highly recommend you check out Andris. Well, he works in OpenAI, and it's pretty nice, code he has there. So here, for the sake of simplicity, we're going to use English alphabets, okay? And a few symbols. So we're going to define a vocabulary that is very small compared to the actual vocabulary of something like llama, etc. So those use very large vocabularies. So the vocabulary of a large GPT, such as GPT-4, could be hundreds of thousands of subwords or more, right? So that would make it pretty complex to wrap our brains around it, whereas this code has 26 or 65, I can't remember exactly. Now, keep in mind, every book that you use will produce a different vocabulary set, right? And so it's not always going to be a fixed number. So this example, I think, is like 65 or something, but you'll have to change that in your code to figure out the size of your vocabulary, all right, for your homework. Does that make sense, guys? Yeah. So this GPT reads in one text file here, which is HuckFin. So now I'm going to get into the code. Okay, so hopefully, you got the main ideas, you've got a picture of what, all these layers, and now we're just going to start going into the code itself, okay? And, I think I like understanding things from scratch. It helps to demystify things. While I love Hugging Face, I think it's awesome. You can do a lot of things. I don't think it's a bad idea to always try to understand the algorithms and how they work, okay? So this is why, in this course, we're covering GPT, right? But I'm also stressing that you can't go from scratch to really powerful tool, okay? All right, so before I begin with the code, any questions, any comments, any issues, anything? All right, so let's start going through this. This will take a while. All right. Definitely, I think it's the best way to start with transformers. So here we have the libraries. Notice there's nothing very surprising about these libraries. Basically, you got your Torch, you got NumPy, Torch NN as NN, which remember, we're doing everything object-oriented. The idea with NN is that it is the PyTorch neural network class, okay? So we inherit that into our own classes. Remember that. So what are we doing there? What is that called in object-oriented programming? Class inheritance, right? Right. So that's exactly what's happening here. And that's kind of one of the things that I really like of how this has been done, is that basically there's a lot of that going on, right? So there's a lot of inheritance of either a function or an inheritance of another class, and then you just modify your thing. So you have something called code decorators that are being used quite a bit, or you have this idea of class inheritance. But that's it. And through that, you're basically able to create your own classes of NNs, right? Leveraging a lot of the code that they have provided, okay? So you'll see this in quite a few examples, and we certainly did a lot of this in 520, okay? The other one here is from Torch NN functional SF. We'll use some of the things required that this provides that we have seen before, loss functions or things like that. All right, so let's take a look at the following. This is the parameters. You can see this is quite a few parameters. The RLHF mini project, I don't know if you've looked at it already, it has a much bigger configuration file. In fact, the models are so big and have so many parameters nowadays that frameworks like Hugging Face now have this construct, config, right? So you have a config file, and the config file has so many parameters, right? And you pass these parameters to the model. So if you start reading through that code, you'll see it's got a config file in there for the RLHF coding. But it actually, it's a good, it's complicated at first, but you know, it's practical to do it this way. All right, so a few things from PyTorch. Obviously, you guys are familiar with this one. To check if you have your CUDA. If you have CUDA, then set to CUDA. The block size here, as I said, is 40, right? So this code is consistent with the diagrams and the Vaswani paper. So that's the n tokens in a sequence, basically. The batch size here is 64 by default. I mean, you can try other things. It's not necessary that you have to have larger batch sizes when training transformers. I haven't looked at, you know, what the batch size was for Llama or something, but I don't think it was super big. Max iterations, you know, number for training 6,000. For printing things, 500, or evaluation. The learning rate is that value, 0.0003. Okay, remember you can play with that, but this should work. Vocabulary size, this is what I was talking about. So I hard-coded this to be 65. And just keep in mind that this may depend on the books you give it, etc. Right? The CODAS is only reads in one file. So what you could do is go on Mac or Linux and just do something like cat several files and redirect into one single file and just create a really big file. I mean, should work, right? Otherwise, you'll have to, you know, figure out how you're going to give it more data. Keep in mind, you also need to give that to calculate the vocabulary size, right? So that's important. All right, a few other parameters. So hopefully now stuff like this should make more sense because you've seen the diagram, right? And we've discussed some of the ideas. So every ID for a given token is embedded to vector of this size. Okay, so this is what I was saying. Go back to the example, all of you as vectors of 3. So it's your height, your weight, and your age, right? So that represents you. That's an embedding. In our case, for the Vaswani paper, it was 512, I believe. Okay, so that's the embedding size. Remember, those weights are going to be originally random, but they must be learned by the transformer itself. That's why I would argue is one of the reasons why you need to give it so much data, because those embeddings need to be really good. Okay. All right. Okay. Number of heads. When you see that, I know Joey tried to implement this last semester. I remember that. So Joey, now I'm sure you can do it now. It's this idea. It's a strange one, actually, because they use this term in transformers for two different things, right? You can create a transformer, and at the end, you add a head. This will become obvious in the BERT models. We'll see that later. I have a diagram for that. And also, when you do this attention thing, which is the example I gave you, you just do it several times, like 8 times, and then concatenate, right? And so maybe the output of each one of those is n by 40 by 512. So now you have that times 8, so that you have a much bigger matrix. So what do? Right? So there's a trick for that as well in the code. We'll get to that. But in general, n head just means the attention heads, how many you want. And layers means the 6 layers. So that should be in the diagram. So 1, 2, 3, 4, 5, 6. They are literally the same structure inside. They produce they take in n by 40 by 512. They produce n by 40 by 512, right? So literally you can just instantiate them in a loop instead of hard coding each layer in the code. and this is how this is done. So that's really an elegant thing, but it's very much how you want to, the only way that you can end up building a transformer that's actually comprehensible once you understand those little tricks. All right, so that's 6 layers, and then the dropout is 0.20, which we covered in 520. If you remember, is when you have some connections that just are dropped randomly, right? So if you have a transformer that has, one simple architecture that has 10 connections, you're training it, you just randomly drop 2. And so now 2 you're not going to learn weights for those. You only learn weights for 8. And then you try that again, you drop another 2 or 3 randomly, and now you only learn weights for the 7 that you have enabled. That's dropout. One way that I like to think of dropout is like this. This example might help you to better understand what dropout does. I want you to do, so this is what you guys as students will do. I say, build a neural network. Whoever gets the highest score gets an A, and you don't have to listen to me for the whole semester. You're going to be very motivated, right? to get the best score. So what are you going to do? You're going to take a neural net and you're going to be like, I'm going to try 10 layers. I'm going to try 3 layers. I'm going to try 7 layers. In each layer, I'm going to try 3 neurons, 7 neurons, 20, so many of those, right? That's what you would do. But then that's going to take a lot of work, a lot of coding. Dropout does that for you, and you only do it once. Because what's happening is you have an architecture that might have 20 neurons and 20 neurons, but if you say drop out of 50, it drops half of them randomly. So now you don't have to make the architecture that has 10 and the one that has 5. Dropout will try all those configurations because it's randomly dropping the connections. Do you guys see that? Does that make sense or no? Yeah. All right, great. So that's what dropout basically is, and this is something that works well, and you'll see it throughout. Questions? All right, so it's 618. So let's just go over this one part of the code, okay? And then we'll come back to the rest, okay? And then, like I said, during the last 20 minutes, I'll just give time to discuss the homework, right? And see where you guys are with that. I do want to do like I like to do like little presentations, right? So I want you guys to come up here for your homework and just really quickly like show what you did. Does that make sense? So just to kind of, you don't have to run it in real time, right? You can just create your Jupyter, save it to PDF or something, and then discuss what you did, show the output basically. I mean, obviously the incentive, the goal of this assignment, beyond understanding this, is to actually train the best or pre-train the best GPT that you can. So that would mean massive amounts of data, or as much as you can, and GPU power, right? So I would encourage you to do that. That's really what we want to see, right? We want to see like, right? Like Jacob, right? Yeah. Yeah. So Jacob, you train it for a week, and we want to see how when you run your GPT, it's actually better at grammar or things like that. So we want to just make interesting observations of what happens when we train it more with better data, and so that's really the objective. All right, so let's take a look at this one. So the next step in the code should be to read in the data. So here you can see you have, you're going to read into text, and it's pretty straightforward. You got some file in there. I have Adventures of Huck Finn from the Gutenberg library. And it's UTF encoding. You read it basically, and now you have the whole text. Now, obviously, this may not be something that you can do if you have a huge amount of books, right? So you need to find a batching system, a batching approach where you're just reading in some books, feeding them into the transformer, read more books, feed them into the transformer. So you're going to have to read and convert and feed it, right? They can't give them all at once, but this just, it's meant to be small. So if you do something where you have a lot of books, you may need to change the code a little bit. All right. So it's 6:20. Let's take a 10-minute break, and then we will keep going with the code. Like I said, hopefully we'll start to understand GPTs.